All right, so what is, or how do we define the instantaneous rate of change? Well, the instantaneous rate of change of an object measures how much a function changes at a specific point. So we said average rate of change is over an interval. Instantaneous rate of change is at a specific point. Now, since we used the secant line to find the average rate of change, we are going to need to use the tangent line to find the instantaneous rate of change. Now, why do we need to use the tangent line? Well, because the tangent line is a straight line that passes through a single point on a curve. So a secant line passes through 2 points, which is great when we have an interval. But the tangent line only passes through a single point, 1 point, which is great when we want the instantaneous rate of change. So we only want the rate of change at 1 point, tangent line. If we want it at 2 points, aka an average, secant line. So therefore, we can use our deductive reasoning skills that in order to find the instantaneous rate of change, we are now going to need to find the slope of the tangent line instead of the slope of a secant line. All right, so tangent lines are great because a tangent line, we said, intersects the curve at one spot. So hey, look at this. Oh, where is it? Come out and play. I blew it. I broke it already. Look at that. There's a tangent line. Woo! Goes through 1 point. But here's the problem with tangent lines. Is that, yes, this is a tangent line, but guess what? That's also a tangent line. And once you know it, there's another tangent line. And wait for it, wait for it, wait for it. Boom! There is another tangent line. So the problem with tangent lines, since they only go through, or since they only intersect the function at 1 point, there are infinitely many ways we can draw a tangent line to go through 1 point. And the question we have then is, well then, which one of these tangent lines represent the instantaneous rate of change? Because they can't all represent that. How can we have an infinite number of instantaneous rates of change? So only one of these tangent lines can actually be the tangent line that represents rate of change. So that's the next problem we need to tackle, is how do we figure out which one of these tangent lines is the one that represents rate of change? So let's go down this rabbit hole. So how do we find the instantaneous rate of change at x equals 1? Well, as it suggests here, we're going to start off with a secant line. So we're starting out with the secant line. And what our goal is that we want to, again, find the instantaneous rate of change at x equals 1. So we want to eventually move this point, and we want to move this point closer and closer and closer until we get it to be on top of this second point. So our entire goal is to move the second point to be on the first point. So if we move this second point closer, boom, there it is. Look at that. New secant line. But it is closer. But if you notice, look how the slope of our lines changed as we move the 2 points closer together. But again, we don't have the second point on the first point yet, so we need to continue moving that second point. So we can move it closer. And again, as you can see with the kind of lighter secant lines, our slope is continuing the change of this straight line, which is why it's so important to find the exact tangent line that represents the slope we're looking for. But we can still do better. So boom, we can get closer. And then as we get closer and closer and closer, eventually, we will get it so that both of the points are at the same x value, meaning that we found the tangent line we're looking for. So this is the tangent line that represents our instantaneous rate of change. And again, if we went back a couple slides, remember there are infinitely many tangent lines, and not all of them represent the instantaneous rate of change. It's this specific one. And we were only able to find this specific one by starting out with the secant line and moving the second point closer and closer to the first point. All right, so what did we actually do here? Well, if we look at what happened at the x's, we wanted to find the instantaneous velocity. We wanted to find the instantaneous velocity at x equals 1. But we needed to start with our secant line, meaning we had two x values. So we started at x equals 3. And then we wanted to move the points closer and closer together. So after 3, we moved our second point to 2. And then we moved it to next to like 1.5. And then we moved it again to maybe 1.25. And then we kept moving that second x value closer and closer and closer to 1. So that's kind of what we did here to create those secant lines. Now, what does this all mean? Well, what happens to our secant line as we get closer and closer to x equals 1? Well, as we get closer and closer to x equals 1, our secant line goes from passing through 2 points to only passing through 1, which was our entire goal. Turn that secant line into a tangent line. What was that, extreme homemaker or whatever? Move that bus. Secant line to tangent line. No, that doesn't quite flow off the tongue as nicely. All right, I'll work on a new game show. All right, and as we just demonstrated, this process will give us the tangent line, and that tangent line that we found will allow us to calculate the instantaneous rate of change. Woo! But the great thing is that, yes, we can do that graphically. We can just casually move points. But how do we do that algebraically? And that's the question. Is if only we had a way that we could move one point closer and closer and closer to another point. So if only we had some sort of, I don't know, mathematical process which allowed us to predict how a function, let's just say, behaves, as, I don't know, we get closer and closer and closer to some, I don't know, number. Shucks, I guess we are out of luck there. Calculus course over. There it is, bin, yes! It is the limit. Look at that. The limit allows us to predict the function of a behavior of a function as we get closer and closer and closer to some specific x value. No way. Crazy. So we can find the instantaneous rate of change. We can convert a secant line into a tangent line by using limits. Yes. There was a point to all that pain I put you through during the first month of class. You might not like the point, but there was a point. So yes, limits is one of, or instantaneous rate of change is one of our applications of limits. All right, so now, great, we can use limits. How do we actually use limits? How does this actually work? So how do we find the instantaneous rate of change using tangent lines? All right, well, we said the instantaneous rate of change is the slope of our tangent line. But what did we actually have to do to find this tangent line? Well, remember, we started with the secant line, or we started with the average rate of change. And then we moved it closer and closer and closer to a specific x value. So essentially what we did is we took the limit of the average rate of change. So therefore, we can find out that our instantaneous rate of change is going to be the limit as x approaches some a value of f of x minus f of a over x minus a at the point x equals a. All right, so let's do our first instantaneous rate of change example. We want to estimate the instantaneous rate of change of the function f of x equals negative 2x, f of x equals negative x squared plus 2x plus 1 at x equals 2. All right, so we know that the instantaneous rate of change is going to be the limit as x approaches a of f of x minus f of a over x minus a. And based on our question, we know that our a value is going to be 2 because that's the point that we want to find the instantaneous rate of change at. That was not worded very well. So a equals 2, so we can start substituting in these values. So we're going to get the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. All right, so then we can start substituting in. So we're going to have the limit as x approaches 2 of negative x squared plus 2x plus 1 minus f of 2 is just going to be 1. And then all over x minus 2. All right, so we can see here that the positive 1 minus 1 are going to cancel each other out, leaving us with the limit as x approaches 2 of negative x squared plus 2 all over x minus 2. Now, if we were to do direct substitution here, we would end up with 0 over 0, which means we need to factor and cancel. So that means I can rewrite this as the limit as x approaches 2 of negative x times x minus 2 over x minus 2. All right, then we can see that the numerator and denominator both have a common factor, so those can cancel out, leaving us at the limit as x approaches 2 of negative x, meaning that our instantaneous velocity at x equals 2 is negative 2. Boom, done. Instantaneous rate of change. All right, so let's take a look at another example for instantaneous rate of change. And here we want to estimate the instantaneous rate of change of the function f of x equals negative 4x squared minus 3x plus 1 at x equals negative 3. All right, so we are trying to find the instantaneous rate of change, so we should probably start out with our instantaneous rate of change formula. And as we said before, instantaneous rate of change is finding the slope of the tangent line, so we're going to use the limit as x approaches a of f of x minus f of a all over x minus a. And in our particular problem, we can see that a is going to equal negative 3. So then we can substitute in our values here. So we're going to get the limit as x approaches negative 3 of f of x minus f of negative 3 all over x minus negative 3. All right, so then next up, we're going to want to plug the x into our function and the negative 3 into our function. And that's going to give us, let's see, negative 4x squared minus 3x plus 1 minus, and then when we substitute in negative 3 into our function, we're going to get negative 26. And let's see, in the denominator, x minus a negative 3 is going to change into x plus 3. And I just made a big boo-boo because I forgot to bring over my limit notation. That is crucial because I have not taken the limit yet. I have not applied direct substitution, so I need to keep writing it. All right. Now after that gaffe, we can continue working. So let's see, we're going to get negative 4x squared minus 3x. 1 minus a negative 26 is the same thing as 1 plus a positive 26, so we're going to get plus 27 all over x plus 3. Then we're going to want to factor the numerator and see if we can cancel out any factor in the denominator. And let's see, we can factor the numerator to be negative times the quantity 4x minus 9 times the quantity x plus 3 all over x plus 3. And now we can see the numerator and denominator both have a factor of x plus 3, so those are going to cancel out, leaving us with the limit as x approaches negative 3 of negative the quantity 4x plus, 4x minus 9. And now we can do a direct substitution, giving us negative the quantity 4 times negative 3 minus 9, which is going to be negative 12 minus 9, which is going to be negative 21, which gives us an instantaneous rate of change at x equals negative 3 of positive 21. Alright, so let's just do a quick review of the two types of rate of changes we have. So first off, we have the average rate of change, which is the slope of the secant line. And we use our standard slope formula, f of x minus f of a all over x minus a. And we find this average rate of change over the interval over the interval a to x. Now, for the instantaneous rate of change, we want to find the slope of the tangent line, which means we take the limit of the average rate of change formula, and we take the limit at the specific instance we are looking for the rate of change. All right, folks, and there you have it, instantaneous rate of change.